Today I'd like to introduce you to the chi-square tests. We're going to look at 3 different chi-square tests. In all of these tests, the data are counts on 1 or 2 categorical variables. And what we want to see in these tests is if the observed counts from the data are significantly different from the expected counts. Where do the expected counts come from? They come from the null hypothesis. We look at how many observations we have in our data. The null hypothesis will tell us how those counts should be distributed, and we compare those expected counts and the observed counts to calculate our test statistic. Now the test statistic has this format. It's chi-square equals the sum of O minus E squared divided by E. So for each category in our data, we take the observed count minus the expected count, square that difference, and divide by the expected count. So we'll get one of these expressions for each category in the data, and then we add up over all the categories. Now this statistic will follow a chi-square distribution with some number of degrees of freedom, and as we go through the unit, we'll look at how we calculate those degrees of freedom. There's a different chi-square distribution for every value of df. Typically, chi-square distributions are right skewed, and as you can see, when degrees of freedom are 8, the distribution is strongly right skewed. But as the degrees of freedom increase, the distributions get more symmetric, and asymptotically they're normal when the degrees of freedom are very large. Let's look at an example of how this all works, and then maybe you'll get a better sense of how all this stuff fits together. Suppose we're looking at a coin. We want to know if it's fair, and to check, we flip it 100 times, and we get 60 heads and 40 tails. Our null hypothesis would be that the proportion of heads and the proportion of tails are both equal to 0.5. That would be consistent with the coin being fair. And the alternative would be that at least one of these proportions is wrong and the coin is not fair. Now what we do to calculate a chi-square statistic is we take the observed count in each category and calculate the expected count in each category, and then calculate the components of chi-square over here using that formula. Now we observe 60 heads. We expect 50 heads. Why? Well, because we have 100 flips, and we expect half of them to be heads. Half of 100 is 50. We also expect to have 50 tails. Half of 100 is 50. Now, for heads, we have 60 minus 50 squared divided by 50. And that'll give us a value of 2. 60 minus 50 is 10. 10 squared is 100. Divided by 50 is 2. So that component of the chi-square statistic is 2. The other component of the chi-square statistic is 40 minus 50 squared divided by 50. That is also 2. So we're going to take these two components, 2 and 2, and add them up, and that will be our chi-square statistic. In this case, it's 4. In this particular situation, the degrees of freedom is equal to the number of categories minus 1. Since we have 2 categories, heads and tails, we subtract 1, and we get 1 degree of freedom. Now, the chi-square distribution for 1 degree of freedom is very strongly right skewed, and it looks like this, asymptotic to the horizontal axis. If our chi-square statistic is 4, the area under that curve to the right of it would be our p-value, and we can find that p-value to be 0.0455, and that's smaller than an alpha level of 0.05, so we could reject our null hypothesis at an alpha of 0.05. If we require stronger proof and our alpha is 0.01, we would not be able to reject in that case. Now you've looked at similar examples in the context of one proportion z-tests, and you might ask yourself, could we have done a one proportion z-test instead? And the answer is yes. The null hypothesis in that case would be that the proportion of heads is 0.5 versus the alternative, the proportion of heads is not 0.5. The z statistic that we get, p hat minus p naught over the square root of p naught times 1 minus p naught over n, when we plug everything in, works out to be 2. The p-value is 2 times the probability that z is greater than 2, and that works out to be 0.0455. That number might look familiar. And in fact, you might notice that the chi-square statistic we got, which was 4, is the square of the z statistic we got, and the p-values are equal. That suggests that the chi-square tests and the z-tests are for proportions are closely related, and in fact they are. Okay, they are both dealing with categorical data, and so they have a lot in common because of that. When the tests can both be performed, they can't always be both performed in a given situation, but when they can be, the chi-square statistic you will get would be equal to the square of the z statistic you would get, and the p-values will be equal. And as we go through studying the different kinds of chi-square tests, whenever we have a chance to do both tests together, we'll try those and see that this is generally borne out.